I'm very happy to introduce Chris Amato. Chris is an assistant professor at Northeastern University, and he has done a lot of really cool work on robotics and some game playing. And today he's going to talk about multi-agent RL.
Thank you very much. So in the title of my talk is Scalable and Robust Multi-Agent Reinforcement Learning. I want to thank in particular two students. These are the students who mainly did the work that I'm going to talk about. One is Shaigun and the other one's Yu Chen. And I'll also say, I don't know where Sam went, but Sam, there he is. He led very nicely with the ending part of his talk into the stuff that I'm going to talk about here, because I'm going to focus on the multi-agent learning stuff, the multi-agent reinforcement learning. And if he didn't convey it enough already, I think we all kind of know that there's going to be multiple agents everywhere, right? There's already becoming lots of agents, robots or otherwise, that are helping us out in our daily lives, whether for drone delivery or autonomous cars. Like typically we think of an autonomous car problem as a single agent problem, but there's going to be lots of autonomous cars, and they're going to need to coordinate with each other in order to really navigate the streets and optimize where they should go, right? And things like UAV surveillance or even home robots, right? Nowadays, the home robots are becoming so sophisticated that they coordinate with each other in order to make sure that your house is as clean as it can possibly be, for instance, right? So there's lots of these kind of domains that we can think about where we're going to have multi-agent systems that need to do learning rather than just a single-agent system, as well as video games, which is also a cool application, like Sam said. But in these multi-agent domains, we're going to have lots of different types of uncertainty, which I think both Sheila and Sam set up nicely before as well. Right? We have the regular outcome uncertainty that we have in a typical MDP. Real-world domains always have sensor uncertainty, so we're going to have partial observability often in these domains. And multi-agent domains often also have communication uncertainty. So like if I have home robots that are made by different manufacturers, for instance, they're not going to always be able to communicate with each other. Or if I'm doing search and rescue or surveillance in dangerous domains, we don't have perfect communication. They can't communicate with each other to have a centralized kind of solution here. So there's going to be these three types of uncertainties that could exist in any of these different domains. Right? In some domains, some of them may not exist. In other domains, maybe all three of them will. So for these type of problems, the common kind of representation for the cooperative case for thinking about these different types of uncertainties. Again, we can think about subclasses or even one superclass, I guess. For modeling these cooperative agents here is the decentralized, partially observable Markov decision process. It's decentralized because now we have this set of agents that's operating in a decentralized fashion. It's obviously partially observable because of the sensor uncertainty. So it's just like a multi-agent extension of the MDP and the POMDP frameworks. So now we have this set of agents here, for instance, our robots, and at each step, they're going to take some action. It's a cooperative problem, so there's a single joint reward that's generated for the team of agents. Each one of them, though, gets its own observation, and then they have to make decisions, choose what to do based on those observation sequences that they're going to get. So a little bit more formally, right? So again, it's an extension of the MDP and the POMDP frameworks. So that we have our agents, our set of states. And then each agent has a set of actions that they can take. There's a transition model that depends on all the agents. So the world state depends on what I do and what you do, right? The reward model depends on, again, what I do and what you do. So it depends on everybody. There's a set of observations that could be different for all the different agents. But the observation model, again, depends on possibly all the different agents in the world state. And then we have a discount factor. So all these functions depend on all the different agents. And solutions for these problems could be anything. But here we need to remember history because, again, we're in partial observable situations. So we want to try and map our different possible histories to the different actions that we may want to choose, because we don't have access to the true state of the world necessarily. So we can have lots of different policy representations. We can have direct history to action mappings. We could have tree-based representations, finite state controller representations, recurrent network representations. And there's one of these representations for each of the different agents so they can operate in a decentralized fashion in the domain itself, right? And then once we have something like this, we can evaluate the set of policies, one for the different agents, using various types of Bellman equations. This is a Bellman equation for the tree or the finite state controller representation, but you could also just think of V of H here as well, which depends on the immediate reward, the transition probability of the system, observation probability of each agent, and then the next value that you can get after that, right? So, and the goal is just like any MDP or POMDP problem, we're trying to maximize expected cumulative reward over that finite or infinite horizon. So if there's any questions about any of this stuff at any point, feel free to ask. I'm happy to try and clarify things. Okay, so now, like I was talking about, so just to make things more realistic, we can think about all these different types of uncertainty. So this model is very general, right? We can consider any type of problem, any type of multi-agent problem that you can, cooperative multi-agent problem that you can think of, we can represent using this framework. It's a very common framework for planning and learning in multi-agent environments. The only more general framework that is typically used is for the competitive setting or possibly competitive setting, is when each agent has its own reward function. That's the parse-observable stochastic game, which I'm not going to talk about today, although some of the methods do apply in that case, so I'm happy to answer questions about it if people want to know. But I'm going to focus on the cooperative case. But it means that this generality of the representation means that we have to consider the parse observability and the other agents in the solutions to the problems. Okay, so that's essentially what I'm going to talk about today, is how do we learn solutions for this model, the Dec-POMDP model. And we want to learn solutions that are scalable to large domains. And then we also want to remind me what time I'm supposed to finish. Sorry. Perfect. Thank you. And then how do we integrate deep reinforcement learning methods into the multi-agent reinforcement learning domains and scaling to large horizons as well. So we'll talk about different methods to do these kinds of things. So first, we're going to focus on decentralized learning. So like I said, using Dec-POMDP models is a common framework for multi-agent reinforcement learning. Most of the methods, though, do centralized learning for decentralized execution. So all the learning is done offline in a centralized fashion so that they can generate a set of policies which can then be executed online in a decentralized fashion. But this is problematic in a couple of different ways. One, that in order to really continue to learn online, you need to be decentralized, right? Because execution is decentralized. So in order to learn online, you need to learn in a decentralized way, which means that each of the agents is continuing to learn while the other agents is also learning at the same time, are also learning. This decentralized learning is potentially more scalable as well because it means that there's less information that all the different agents have to keep track of. Right? You keep track of your own history information separately, right? And just are generating a policy directly from your own history information to the actions that you want to pick. So this is nice because it's potentially more scalable, and we can directly apply, if we'd like, naively at least, single agent RL methods to each of the different agents in the domain. But this is problematic because now the problem is non-stationary from the perspective of a particular agent. Right? I'm learning while at the same time you're learning. So this is changing what it seems like the environment is doing. Right? So I need to reason about this non-stationarity or do something about this non-stationarity to make these methods not be quite so naive and work well in practice. Okay, so the first method that we came up with is a combination of some of these ideas, right? Using some ideas from multi-agent reinforcement learning and using some ideas from deep reinforcement learning, combining them in a way in order to allow the methods to perform well in these type of domains. So the basic idea here is that we're first using the idea of hysteresis, which was originally developed a while ago for the non-deep case, the tabular case of multi-agent learning, where we now have two learning rates. So instead of just having one learning rate, we have a learning rate that's different depending on what the TD error is. So for the negative case, when it seems like something bad happened, right, we use a smaller learning rate. So that is, when something bad happens, we're assuming it's because the other agent was exploring, the other agent, or doing something stupid for some reason. So we want to kind of discount that. we don't want to learn from that quite as much because that's a random bad thing that happened that we don't want to really consider too much. So we use a smaller learning rate there so we can be more optimistic so that we can hopefully coordinate on doing the good thing, right? So we want to learn from these cases in which all the agents do the right thing at the right time and maybe not learn quite as much from cases in which there's random exploration by any of the other agents, which is going to cause a negative TD error in these cases, right? So we have these two different learning rates for these different cases, right? So then if we have positive TD error, right, then we're going to change in a positive direction. We have the regular learning rate, and then when we're changing in the negative direction, then we use a smaller learning rate. So this is going to make it possibly a little bit too optimistic and can run into issues with stochasticity. But by adjusting these rates over time, we hope to be able to converge to a good value. Okay, and then one common thing that people do, before we get there, I guess, is, so for the deep case, right, we're going to build on DQN. I think everybody knows what DQN is in this audience. And then, again, a common thing that's done, I think Matthew's in here somewhere as well. So back there. So a common thing that people also do, right, is an extension to DQN or any of the methods to stick a recurrent layer in there. So now this is going to allow us to consider history and take advantage of this sparse observability, right? So basically, this first approach, the hysteresis, is going to help us to deal with non-stationarity. DQN or deep methods in general are going to help us scalability in the input space. Right now, we can deal hopefully with larger observation spaces, and the recurrent layer of using DRQN is going to help with the parse observability. Okay, and one other thing. So in these cases, so when we're training these recurrent layers, right, we need to sample trajectories. So previous methods have not used the replay buffer prior to this because it caused instability in learning, because if each of the agents is pulling from a replay buffer separately, this caused the gradients to have issues and caused the learning to be unstable. So in this case, what we did was we generated replay buffers that were synchronized across the agents. So we could sample random seeds beforehand, right? And then when we would, during the learning phase, right, we could think about the time, the episode, and the agent, so that when we're sampling the trajectories from each of the different agents, they're sampled from the same time steps so that we can be more robust in our learning. And again, we can do this in a decentralized way, and this thing was called a concurrent experience replay trajectory, or CERT. Okay. So using these methods, we could compare with our method with the previous basic method. So just using, without hysteresis and without the CERT versus using hysteresis and the CERT. So what we essentially see in these cases is that our method is scalable to larger domains. So you see what happens here. So then on top is the previous methods. And this is a target capture domain. So we have our two agents have parse observability as to the location of that other agent. That red agent flickers. And we need to try and catch that other agent. If we're in the same square, we get a reward of 1. And so in these cases, for small domains, they get about the same value. So 3 by 3, 4 by 4, they're about the same. But then when you start moving to 5 by 5, without using hysteresis and the CERTs, learning becomes unstable. And so it doesn't do so well. And then for 6 by 6 and 7 by 7, the learning doesn't really happen for the other case. Whereas for our case, then we're able to learn for larger domains and get good values. We can actually scale to larger agent sizes as well. I just didn't include those results. And we also, in this paper, had a version that tried to solve multitask problems as well. But again, I'm not including those results in here as well. Okay, but that method works really well. It can solve those problems, but has some issues scaling up to problems with long horizons, right? And these long horizon problems, especially with multiple agents, it's very unlikely that those agents are going to coordinate on doing this thing that's very far out into the future. So one thing that we can do, which I think Sheila mentioned as well, is we can use an idea of macro actions. right? So in this particular problem, for instance, right, if we're trying to coordinate, for our domain, I should change these things, but if we're trying to coordinate so that we need to deliver tools to these different people, which are a bunch of co-authors, if we need to think about it at a low level, right, for each of these agents, they might need to move here, right, and then come back, and then go over here and ask the PR2 for something and continue on. Do this. The horizon of this problem is going to get quite long quite quickly, and really, we don't, for this type of problem, we don't need to, there's no coordination at that level. Like navigation, there's very little coordination that needs to happen, right? So we can kind of think of the problem where we can break it up and have like single agent parts and multi-agent parts, right? And from the single agent part, we can have a hierarchical kind of method where the single agent part can be navigation independent of the other agents. We can have low-level collision avoidance that they can learn, but really it's just navigating from one location to another location. We don't need to do multi-agent reinforcement learning at that level. We need to do multi-agent reinforcement learning over the level of how do they coordinate, but we don't need to do multi-agent reinforcement learning over how they navigate from point A to point B. Right? So we can build macro actions, which is, in our case, a type of option that we can have for the different agents. We can build those lower level macro actions, and then we can do learning at the higher level over those independent single agent macro actions in order to scale to these large domains. Sometimes these are given to us in advance, like navigation controllers for robots or grasping controllers for robots, these kind of things. There's already very good solutions for those type of problems, and we could just use those directly. Other times we can talk about trying to learn those as well. Yeah, we call this a macro action, Dec-POMDP potentially, and have slightly different notation. So I have a slide on that slightly different notation as well. So now macro action is an M, and a high-level observation, maybe it's a macro observation, is a Z, and then our policy representation will be over those M's and Z's instead of those A's and O's that we had in the previous case, right? And otherwise, the representation will be essentially the same. The evaluation gets more complicated now because it depends on time. I'm not going to go into this in too much detail, but I'm happy to talk about it if people want. Is that technically, in order to do the evaluation, becomes a semi-Markov decision process because we have to reason about how much time. So after time step k, right, this will complete after time step k and will be in state S prime after taking a macro action in particular state S. So it becomes a semi-Markov process rather than a traditional Markov process. But this is the general model that you would get in this case. Okay, so all right, now, so this idea of macro actions exists. How do we do learning for these cases, right? So all the current deep multi-agent reinforcement learning methods, they assume synchronized or primitive actions. None of them make use of these asynchronous macro actions in this case. So it isn't clear how to incorporate this idea of asynchronous actions into the deep MARL methods. So let's think about how we'd like to do this, right? So the basic idea is that in this case, we will make the assumption that we only get the information at the macro action level. At each time step, we get information about which macro action each of the agents is executing, or in the decentralized case, that particular agent's executing, what particular observation they see, and the joint reward, right? So we get this information every primitive time step. So at the first time step, agent 1 gets this information, agent 2 gets this information, right? So it gets a particular macro observation, the macro action that it's currently executing, and then whether there's a new observation, if it's terminated or not, right? And each of the different agents gets this information. Sorry, I'm ignoring the people over here. I should point to stuff over there as well. Wander that way. And then this continues, right? So the next time step, we're going to get that information. The next time step, we get this information. Like I said, I'll walk over here. We're accumulating this information per agent in terms of the reward. So that's why the sum is happening. So the sum is happening just to try and, for each agent, you're accumulating the reward while the macro action is continuing. And then when the macro action terminates, then you no longer accumulate the reward and you start reaccumulating the next reward from the next time step. So we can generate this trajectory. This is the trajectories of the agents that are generated over time at the macro action level. And we have all this information for these 10 time steps. So we can generate that. And then from there, we can, we call these things max certs, just an extension on the original cert idea. So in order to train the recurrent network, we have to sample this sequence from these trajectories. So maybe we sample this particular set here between 3 and 8. And then from there, now for each of the different agents, we'll only have a particular view. So agent 1 will only have a view of its particular trajectory. Agent 2 will have its particular trajectory. And then in this case, right, so now we need to identify when the macro actions change. So we don't need to have all the information about all these time steps. We could potentially, but we're identifying when the macro actions change. And then in our case, we're going to throw away the time info. We're just going to compress them so that we're ignoring the time info. You could imagine you keep that time information, but in our case, we're throwing it away. So now we just have the macro action info for what happens within those time steps. Is this making sense? Yeah, okay. So once we have this, now we can essentially just throw this into the method that we talked about earlier. So the Dec-HDRQN, there's too many letters there, is the method that we talked about before, the hysteretic deep recurrent queue network that happens to also be decentralized. So we can throw the macro action level information directly into that algorithm so that we can continue to learn in a decentralized way. So these are all calculated in a decentralized way. I'm again ignoring the folks over there. So that we can get this information for agent 1 and then this information for agent 2. And we can put those into the previous algorithm. And it gives us this particular loss function, which is just this is the double DQN version, but it doesn't matter that much. So we can put in the loss function in order to try and learn the Q functions in that case. Okay, so this is the decentralized version. The decentralized version is actually simpler than the centralized version. So for the centralized version, the idea is, so we're assuming now that we have perfect communication. We're going to just do centralized learning here. So in centralized learning is potentially useful in the cases when we do have, in fact, full communication online as well as offline. Or there's a bunch of methods that try and use the centralized values as an interim kind of to try and learn better decentralized values that can be learned to execute online. So in this case, we can do the buffer in a kind of centralized way. So where we're going to do the same kind of thing as before, but here just directly identifying when the macro actions end, which we can do at the beginning or the end. But the buffer is the same. It's just we only have this one joint reward that we're accumulating here, rather than the different rewards for each agent, which we have in the decentralized case. And the trick here is that we identify when the macro action ends for any agent, right? This is the problem in this case. In the centralized case, in the decentralized case, it's clear what it means for termination, right? Like if I terminate, then I stop accumulating my reward. But in the centralized case, it's not clear because it's asynchronous. There's really unlikely to be a chance when both agents terminate at the same time. It's always going to be one agent terminates and one agent doesn't. So you have to figure out when you decide that, otherwise you have just one big action, right? So you have to break it up into particular subsets and make sure that you're not overcounting in the reward. So then what we do here is we assume that a macro action terminates when any agent's macro action terminates. So this is, now agent 2's macro action terminated, so this becomes one macro action here, and then after this, now both of these agents terminated, so this is another chunk, right? And then on the next step, agent 2 terminated, so that's another chunk, right? So we can break it up in that sort of way in order to deal with the asynchronous actions that we have here. So we can generate that into a centralized buffer in this particular case. We remove the time info again, just like we did before. And now we can learn in a centralized way using these centralized experiences. In this case, this is just the double DRQN that we use for learning in that case. And there's one other kind of thing as well, which we can use in the centralized case, is when we're doing the argmax, what happens here is that remember that not all agents get to change their macro actions at each of those steps, right? Because what we know from these trajectories is that only some of the agents stopped, and therefore only some of the agents were able to change what they were able to do. The problem's asynchronous. So the basic idea of this conditional target value prediction is we fix the macro actions for the agents that don't change, and we only allow the argmax to go over agents that do change, right? So we only consider agents that are able to change their macro action at that particular time step based on the trajectory information that we have. Yeah. Okay. Lots of replay buffers, but the idea is relatively straightforward, I think. Okay, so once we have this idea, now we can talk about results, and obviously we want to try and compare on the previous domain as well. So this is the previous domain, the target capture domain. And in this case, we didn't learn the macro actions and the macro observations. We set them for these problems. And in this case, it's pretty straightforward to set. The original actions are just up, down, left, right, and stay. And the macro actions in this case is you get an observation of the target that flickers. So the macro action is to move towards the last observed location of the target. Seems like a pretty straightforward thing to do, right? So if we do that, in this case, the problem is so simple that for a 4x4 and a 10x10 version of the problem, so for the macro action case, there's very little learning that even needs to be done because the macro actions are pretty good and the problem's pretty simple. So that in both of these cases, the primitive version and the macro action version learn the same thing, but the macro action version, as you can imagine, is going to learn it much faster. But then we can think about more complicated problems. This is a box pushing type problem where these are waypoints that the agents can move to, and we have these two robots. There's a bigger box that they can coordinate to push on, or there's these smaller boxes that they can push independently, right? So they have to both push this together at the same time in order to move the box, and they get a reward for moving it to the goal up at the top. So we can look at the decentralized case here, where we have the primitive actions and the macro actions for this case. So again, in the macro action case, we can move to these different waypoints. We can push these kind of things. In the primitive case, it's up, down, turn, straight, push, things like that. And the values here are for the 10x10 and the 30x30 case, where in the primitive action version, you see here the primitive action learns a little bit, but very slowly and does not do very well at all. Whereas the macro action version can learn relatively fast. And then this is the optimal value. That's this dashed line up here. So then it can pretty quickly get to the optimal value for this problem. And then we can compare it with the centralized method. And as you would imagine, the centralized method is going to do better than the decentralized method in this particular problem because it has more information. It can coordinate explicitly. So the centralized method learns even faster than the decentralized method for this problem. Yeah, okay. And then we can look at a more complicated problem. This is the one human version of the problem. We looked at a couple of different versions, but now this is a multi-robot problem. It will be at least a multi-robot problem, where we have, this is going to be a robot that is at a desk that can try and find objects that are on the desk. And then these are two delivery robots, similar to the picture that I showed earlier for, there's a human in a workshop here that's doing some task, and then we need to try and figure out which objects to get to the person at different times based on what their tasks are doing. So we need to monitor them and bring them the right objects at the right time in order to make sure that they can most efficiently complete all their tasks that they need to do. And then, so we compared our decentralized method and our centralized method for this particular problem. The centralized method could learn pretty quickly and converge to a near optimal policy, while the decentralized method didn't do so well in this particular problem. But the reason why it didn't do so well isn't necessarily a problem with the method itself, rather than a problem with the problem itself. The problem is just really hard, and the information that you get in the decentralized case is not enough to make it so that you can coordinate well. in this particular case, the information that the fetch robot had in this case was just not enough, and the data that it got wasn't enough for it to be able to figure out what the right objects were to give the particular humans in this case. So there's certainly problems in which there isn't a good decentralized solution that you can get in these cases, whereas obviously the centralized solution will be better. Okay, so then we ran an extension of our method on a real robot task. And this is the real robot task, where we have our fetch robot and our 2 turtlebots. There's our human worker that's over there that needs to be monitored. And this is actually extension of the method that I said on the previous slide. So it's not quite the centralized or the decentralized method. It's pretty much similar to the centralized solution, though, where they're monitoring the person and now bringing the person the first object or the first tool that the human needs. The human's trying to build this table and needs the tape measure and then the clamp and then the drill in order to be able to build this table at the most efficient manner. This is obviously a simplified version of the problem. You can imagine many humans and many more robots and much more complicated. But this stuff is hard to get to work on a set of robots, so you want to start simple. So here you see that it gave the person the tape measure, and now the next robot's getting the clamp. So we'll bring the clamp to the person while the fetch is giving the last tool to the other robot there. So the clamp can get brought to the human here. They can clamp the table in that case. Table is sufficiently clamped, I guess. And then they can finally have the drill there, and they can use the drill to finish drilling all the screws into the, oh, there it goes. Drilling all the screws into the table in order to finish the beautiful table. Yay, done. Okay. So I think I'm quickly running out of time. So I will skip this method, I think. Right, I think I have 5 minutes left. Yeah. So I'll skip this method. This is trying to learn, it's a non-deep method for trying to learn controller-based representations for the decentralized macro action approach here. So I'll skip this, even though it does have a cool robot video that I wanted to show. But you can look at my webpage for the robot video where they're doing, I'll just say that this is search and rescue, where there's a aerial vehicle and a bunch of ground vehicles. An aerial vehicle can see more stuff than the ground vehicles, obviously, but the ground vehicles have to bring things to the people and rescue the people. So they need to coordinate and communicate with each other in limited communication range in order to be able to figure out where the people are and get to them most effectively and rescue them most effectively. So that's the particular domain that we were looking at there. Okay, and then, so maybe for this audience, I don't need this slide, but I like this slide. So people often ask, right, or often try to use DeepRL nowadays. It's quite popular for trying to solve many different problems, and it's helpful in some ways, but it's certainly, especially in these partially observable multi-agent problems, doesn't solve all the problems. Right, so there's a number of big issues that some of which have been studied in the past, and some of which there aren't good solutions for. There's a bunch of good issues that still need to be solved and be able to deal with solving these large, interesting problems. So one of which is centralized versus decentralized learning. So the stuff that I was talking about today was a decentralized learning case, which is the hardest case. It's like all the agents are acting online based on very limited information that only they have. Right? It's quite hard to learn in that case. So what are the best methods that we can use? How do we use those signals in a better way to do things that are more sophisticated than hysteresis to be able to deal with the non-stationary that we get when we're doing decentralized learning? Right? And in the centralized learning case, what's the best way of balancing off the centralized information in order to learn well? So there's a bunch of methods that are popular for using centralized value functions to help learn decentralized solutions. But that can often be a bad thing. The centralized value function can make you do stuff that you just can't do in the decentralized case. So we need to be a bit more, think more about what the best methods are to use in that case as well. Obviously, again, the deep methods are popular, but don't always have very good sample efficiency. So how do we use them online in order to be able to learn quickly? And dealing with partial observability, right? So just using LSTMs in there is an easy solution, but it's probably not the best solution. How can we better use partial observability, take advantage of that, come up with other structures in order to be able to learn well and deal with the partial observability that exists in these different domains? So I will conclude there by saying, so for the multi-agent reinforcement learning problems, one of the most general representations is this Dec-POMDP, decentralized POMDP, where it considers the outcome, sensor, and communication uncertainty in these domains. So we can model any multi-agent coordination problem this way. So I talked about a couple different methods. One, just integrating deep learning with the multi-agent reinforcement learning under this framework, and using macro actions as an abstraction to improve scalability in the horizon here. Yeah, and using learning methods, right? And so these methods, they also apply in the subclasses as well. So if we assume that, well, even in the superclass, some of them, right? So if we don't have uncertainty, or if we have different reward functions, some of these methods can still work. And these are some methods that we've started to develop. But like I said, there's lots of cool open questions that still need to be solved. I'm sure Sam and his team will solve many of them, but there will still be plenty open for other people. So I'm happy to talk about them as well afterwards if people have questions.